This video is going to show you how to convert from miles to kilometers using only the Fibonacci numbers shown here. And the nice thing is, and the reason I love this so much, is once you know the Fibonacci numbers, there's nothing else to memorize. Here's what you do. First, you make the Fibonacci numbers. So you start with 1, 1, and every single number is the sum of the previous two. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Now, take any two consecutive numbers. So for example, 3 and 5 are right next to each other, and you can interpret this as a miles to kilometer conversion. All you do is say that the lower number, 3, is 3 miles, and the bigger number, 5, is 5 kilometers. So 3 miles is approximately 5 kilometers. And it's not exactly right. 3 miles is not exactly 5 kilometers. It's actually 4.8, but it's very close. And the great thing is you can do this with any two. So instead of doing it with 3 and 5, you can do it with 5 and 8, and it's even more accurate. So 5 miles is approximately 8 kilometers, and that's even more accurate than the 3 to 5. 8 miles is approximately 13 kilometers, and that's even more accurate than the 5 to 8. And you can go on and on and on and do this with any Fibonacci number pair that you want. So I love this trick. I use it all the time. Somebody told me once, they're like, what if you need to convert a number that's not a Fibonacci number? Well, of course you can use this as a starting point. So a really common one for me, I'm Canadian. If I'm driving my car in the US, a common speed limit is 55 miles an hour. What is 55 miles an hour on my speedometer? Well, I multiply by 11 and 5 becomes 55 and 8 becomes 88. So 55 miles an hour is approximately 88 kilometers an hour. So whenever I'm driving in the US, I'm always doing these Fibonacci numbers. I'm adding them, I'm multiplying them in my head to make whatever number I need. Okay, now if you have the soul of a mathematician, you will ask, why is this true? And mathematically what's going on is we have the ratio of Fibonacci numbers, the n plus first Fibonacci number to the nth Fibonacci number. That ratio is approximately the ratio of 1 mile to 1 kilometer. And if you just cross multiply, you'll get what we had before. But why is this true? Okay, miles and kilometers were invented long after the Fibonacci numbers. So actually this is a kind of a coincidence. And what's really going on as this ratio of Fibonacci numbers is converging to something called the golden ratio. And as n gets bigger and bigger, this ratio, Fn plus 1 over Fn, is getting closer and closer to the golden ratio phi. What is phi? Well, you can define it as 1 plus square root of 5 divided by 2, and it's approximately 1.618. People have said it has many magical properties through the years, and it has some interesting things to do with how irrational it is. You might ask, okay, well, why is it true that the Fibonacci numbers, when you divide them like this, Fn plus 1 over Fn, why does it get closer and closer to phi? And in the past, I've done long lecture-style videos finding an exact formula called Benet's formula for the Fibonacci numbers, and you can use that to show its connection to the golden ratio and why you're getting this ratio coming out. So I'll link those in the video description if you want to check out either some linear algebra way to do it, or there's a cool calculus trick to do it. But in this video, I'm going to show you a much simpler way because I figured out how to do it in just one Desmos graph. Okay, so this Desmos page is my picture proof of why the ratio Fn plus 1 over Fn, the ratio of two consecutive Fibonacci numbers, why does that get closer and closer to the golden ratio phi? And so here's the picture proof. What it is a cobweb diagram, I'll explain what that is in a second, between these two functions, 1 plus 1 over x and the function y equals x. If you have these two functions, 1 plus 1 over x and y equals x, you can alternate between them and make this little cobweb picture. So you start at some point, we're going to start at x equals 1 right here, and you alternate between the two functions. You go from one function to the next function and back and forth, and it generates this little sequence of x's on y equals x. So it starts at x equals 1, then it's going to go to x equals 2, then it's going to go to x equals 3/2, and so on and so on. And it's going to spiral around. You can see it spiraling in, and it spirals in closer and closer to where these two functions intersect. And that intersection is exactly at the golden ratio, 1.618. So what does this have to do with the Fibonacci numbers? Well, actually, what I'm going to show you is that this cobweb thing is generating exactly the Fibonacci numbers. So the first ratio over here is 1 over 1, the ratio of the first two Fibonacci numbers. The next one is 2 over 1, the ratio of the next two Fibonacci numbers. Then 3 over 2, then 5 over 3, and then so on and so on. So as you do this cobweb diagram, you're actually just generating Fn plus 1 over Fn, and you can see visually that you're spiraling in towards the golden ratio. Okay, so now let me explain where this function, f of x equals 1 plus 1 over x, comes from. And it really starts with the rule for the Fibonacci numbers that says that the next Fibonacci number is the sum of the previous two. So Fn plus 1 is the sum of Fn plus Fn minus 1. Now if I take this equation and I divide both sides by Fn, I'm going to get exactly what I want. fn plus 1 divided by fn on the left. So here I'm just dividing by fn everywhere. And on the right, I have fn divided by fn. That's just 1. And I have fn minus 1 divided by fn. You might notice fn minus 1 divided by fn is backwards to what we want. We want the ratio of the next Fibonacci number to the previous one. So this fn minus 1 over fn over here is not the right way. To fix it, you put a 1 over. So this is equal to 1 plus 1 over, and then you have the ratio fn over fn minus 1. And what we've just shown is that if you look at the ratio of two Fibonacci numbers, it's related to the ratio of the previous Fibonacci numbers through this function 1 plus 1 over x. So in other words, what we've shown over here, make a little arrow going down here, we've shown that fn plus 1 over fn is the function f, oh my goodness, too many f's, but okay, we've done an f of fn divided by fn minus 1. So to get from one ratio to the next, you just apply this function 1 plus 1 over x, and it will convert the previous ratio of Fibonacci numbers to the next ratio of Fibonacci numbers. So again, as an example, if you start with the ratio, the Fibonacci numbers 1, 1, 2, the ratio of the first two numbers here is 1, right? And if you want to get from the ratio of the first two Fibonacci numbers 1 to the ratio of the next two Fibonacci numbers, which is 2, you apply the function 1 plus 1 over x. 1 plus 1 over 1 takes an input of 1 and outputs 2. If you take the input of 2, you'll get 1 plus a half, which will be the ratio of the next two numbers, which is 3 halves. And if you do 1 plus 1 over 3 halves, you'll get the next ratio, which is 5 thirds. So basically, we're taking this function f, and we're applying it over and over and over again. That will give us the ratios of the Fibonacci numbers. And this Cobweb diagram is doing exactly this idea of applying the function f over and over and over again. What you're doing is you're starting with 1, and you're feeding that into the function f. That's exactly doing this up move. So this will be 1, this will be f of 1. And now, to take the output of f of 1 and treat it as an input, that is exactly what doing the horizontal slice of the Cobweb diagram does. So then I take the value f of 1, and to feed it into the function again, I convert it to an x value, and then I feed it back into the function. This will be f of 1. And so this Cobweb diagram is really doing this repeated application of the function 1 plus 1 over x. It does it over and over and over again, and you spiral in. That's what makes you spiral in towards the golden ratio. Okay, so a quick little bonus feature for you here. What if we lived in an alternate universe where the ratio of the first two Fibonacci numbers was not 1? Well, then we could slide this little starting point around to whatever it was. So you could imagine if Mr. Fibonacci, instead of starting with the numbers 1, 1, they started with two different numbers as their starting numbers, then we would get a different sequence of numbers. And in fact, there is a famous sequence of numbers called the Lucas numbers, and they start with 2, 1. So they go 2, 1 as the first two numbers, and then every number is the sum of the previous two, just like Fibonacci now. So 2, 1, 3, 4, 7, ... And you might ask, okay, what about the ratio of Lucas numbers? Well, it turns out we have the same rule that every number is the sum of the previous two. So all we have to do is take our slider and slide it to the starting point here. Here, the ratio of the first two numbers is a half. So we can say, what would happen in that universe? We'll slide our starting point to x equals a half, and you can see, okay, we have to zoom out a bit because, you know, the ratios get crazy. They go all the way up to 3, which is just outside of our view, but they spiral back in, and they still spiral towards the golden ratio. So in fact, any Fibonacci-like sequence that you make will always have a ratio that is spiraling in towards phi, and that's because no matter where you start your ratio, you'll always spiral in towards the golden ratio. That statement is true for all except for one extremely special Fibonacci-like sequence. For a very, very special, exactly one special starting value, it does not spiral in towards phi, it does something else. And I will leave that for the comments if you want to discover what starting point, what special starting point does not spiral in. Okay, I will leave that to you to figure it out. If you can answer this question, you are very close to coming up with a proof for what is the formula for the Fibonacci numbers. So if you take this special value and you take what we've done so far, you can do some little math magic and get the exact formula called Benet's formula. But again, I'm not going to do that in this video. I've done that in some previous videos, so I'll just stop here.